We are on a collision course in mutual descent towards our neighboring large galaxy Andromeda, a system of several hundred billion stars. Our cosmic neighbor, the Andromeda Galaxy, is the nearest spiral galaxy to the Milky Way and is expected to collide with our galaxy. It is anticipated that this event won't happen for another 4 billion years. However, a shocking signal has been sent back to Earth by the James Webb Space Telescope, indicating that the collision will occur far sooner than expected. Furthermore, after a century of assumptions, the data from the James Webb Space Telescope has changed our knowledge of the Andromeda Galaxy by revealing startling and unexpected details about its true nature. This discovery has sparked a flurry of excitement and speculation within the scientific community. Is this an answer to our attempts at interstellar communication? Or does it indicate a celestial occurrence that is still unknown? And what happens when Andromeda strikes Earth in the Milky Way galaxy? Join us today as we explore the reason for the alarming signal received by the James Webb Space Telescope from the Andromeda Galaxy. Our galaxy, the Milky Way, belongs to the local group of galaxies and is a barred spiral galaxy. To find this galaxy, you would need to look up at the night sky in the direction of the star constellation Sagittarius. Its galactic center is very faintly visible there. All stars, nevertheless, are actually part of the Milky Way and are visible to the naked eye from Earth. The rotational speed of the Milky Way is comparatively faster than that of many other galaxies. Although there are billions of galaxies in the universe, this one has taken an astronomically long time to uncover and understand due to the restricted scientific instruments available at the time. Astronomers initially knew very little about the Milky Way. The first recorded observations of the Milky Way date back to ancient civilizations. The Greeks named it Galaxius Cost, meaning milky circle, due to its milky appearance in the night sky. However, it was not until the invention of the telescope that we began to understand its true nature. With the invention of the telescope in the early 17th century, astronomers like Galileo Galilei were able to observe that the Milky Way was composed of a vast number of stars. This was a significant step towards understanding the structure of our galaxy. In the early 20th century, the nature of the spiral nebulae was the subject of the great debate between Harlow Shapley and Heber Curtis. Shapley argued that the Milky Way was the entire universe, while Curtis believed that the universe consisted of numerous galaxies like the Milky Way. The debate was resolved by Edwin Hubble in the 1920s when he identified Cepheid variable stars in the Andromeda Galaxy, which allowed him to prove that it was indeed an independent galaxy outside the Milky Way. Edwin Hubble's work on the Andromeda Galaxy also led to one of the most important discoveries in modern astronomy, which is the expansion of the universe. By observing the redshift of the light from the Andromeda Galaxy, Hubble was able to show that the universe is expanding, with galaxies moving away from each other. This discovery formed the basis of the Big Bang theory. However, Hubble was not the first astronomer to notice this galaxy. Since ancient times, humans have been aware of the Andromeda Galaxy. The Persian astronomer Abd al-Rahman al-Sufi called Andromeda the Little Cloud in his Book of Fixed Stars in 964 AD. He was the first astronomer to see Andromeda with a naked eye before the invention of telescopes. But it wasn't until much later that its full nature as a galaxy was understood. Astronomers sometimes call the Andromeda Galaxy by the name Messier 31 or M31. For a long time, astronomers believed Andromeda to be substantially larger than our own Milky Way galaxy. From an objective perspective, such an error might easily occur since we live in our own galaxy and Andromeda is so large when viewed from Earth. However, that is incorrect. Recent research has brought about a reevaluation of these beliefs. Based on all available data, astronomers estimate that Andromeda is roughly 10 billion years old, which puts it in the very early universe. Its age suggests that its development and evolution had a long and complex history. Our Milky Way galaxy is 100,000 light-years in diameter, but the Andromeda Galaxy is 220,000 light-years in diameter, almost twice the size of our galaxy. Compared to the Milky Way's 250 to 400 billion stars, it has around 1 trillion stars. Although it appears peaceful to the naked eye, astronomers have discovered a violent history and future within it. The active galactic nucleus of the Andromeda Galaxy is one of its most interesting features. The highly active region at a galaxy's center is called the active galactic nucleus, or AGN for short. It can be identified by strong emissions at a range of wavelengths, including X-rays and radio waves. The supermassive black hole located at the center of the galaxy provides the energy source for AGNs. These supermassive black holes are extremely dense areas in space with a large mass packed into a little volume. This black hole weighs roughly 110 to 230 million times as much as our Sun, according to estimates of its mass, which range from 1.1 to 2.318 solar masses. The presence of supermassive black holes like the one at the center of the Andromeda Galaxy significantly influences the dynamics and evolution of galaxies. These black holes not only exert immense gravitational forces but also play a crucial role in shaping the environment around them through processes like accretion and the formation of active galactic nuclei, AGNs. AGNs are among the most luminous and energetic objects in the universe. They are powered by the accretion of material onto the supermassive black hole at the galaxy's center. As matter spirals into the black hole's gravitational grasp, it forms a swirling disk of hot gas and dust. This accretion disk becomes incredibly bright and emits radiation across the electromagnetic spectrum, from X-rays to radio waves. The Andromeda Galaxy's active galactic nucleus exhibits these characteristic emissions, indicating a vigorous process of material falling into its central black hole. This phenomenon not only fuels the AGN's luminosity but also influences the surrounding galaxy's evolution. The intense radiation and energy released by AGNs can affect star formation rates, gas dynamics, and even the morphology of galaxies over cosmic timescales. In addition to its AGN, the Andromeda Galaxy is also known for its large and diverse population of stars. Like the Milky Way, it contains a mix of young, hot stars and older, cooler stars, spread across its vast expanse. Observations have revealed clusters of stars, star-forming regions, and stellar associations throughout Andromeda's spiral arms and central bulge. One of the remarkable features of the Andromeda Galaxy is its satellite galaxies. These smaller galaxies orbit around Andromeda, gravitationally bound to its larger mass. Some of the notable satellite galaxies include M32 and M110, which are dwarf elliptical galaxies found near Andromeda's center. These satellites provide valuable insights into the gravitational interactions and dynamics within the galaxy group. Andromeda's gravitational influence extends beyond its immediate satellites. It is part of the Local Group, a collection of over 54 galaxies that includes the Milky Way, Triangulum, M33, and numerous dwarf galaxies. The gravitational interactions between these galaxies shape their orbits, affecting their evolution and distribution within the cosmic web. Recent advances in observational astronomy, particularly with instruments like the James Webb Space Telescope, JWST, have revolutionized our understanding of galaxies like Andromeda. JWST's ability to peer through dust clouds and observe distant objects in unprecedented detail has unveiled new insights into Andromeda's structure, dynamics, and evolution. One of the significant discoveries enabled by JWST is the identification of stellar populations within Andromeda. By analyzing the colors, brightness, and spectral characteristics of stars, astronomers can infer their ages, compositions, and evolutionary histories. This detailed stellar census provides clues about Andromeda's formation and star formation processes over billions of years. Moreover, JWST has revealed intricate structures within Andromeda, such as stellar streams and tidal tails. These features are remnants of past interactions and mergers with smaller galaxies or satellite clusters. Studying these tidal features allows astronomers to reconstruct Andromeda's history of galaxy interactions and understand how such events have influenced its current state. In addition to stellar populations and structural features, JWST has contributed to our knowledge of Andromeda's dark matter distribution. Dark matter is a mysterious, invisible substance that exerts gravitational pull on visible matter, shaping the large-scale structure of galaxies and galaxy clusters. By observing the gravitational lensing effects and dynamics of stars and gas, astronomers can map the distribution of dark matter within Andromeda. The presence of dark matter in Andromeda is inferred from its gravitational effects on stars and gas. Detailed studies suggest that dark matter makes up a significant portion of the galaxy's total mass, far exceeding the mass of visible stars and gas. Understanding the distribution and nature of dark matter in Andromeda is crucial for testing theories of galaxy formation and evolution in the context of cosmic structure formation. Beyond its scientific significance, Andromeda holds cultural and historical importance. Since ancient times, it has been a subject of fascination and study among astronomers and skywatchers. Its appearance as a faint smudge in the night sky has sparked curiosity and inspired myths and legends in various cultures. The discovery of Andromeda's true nature as a separate galaxy outside the Milky Way was a milestone in the history of astronomy. It expanded our understanding of the cosmos and our place within it. By recognizing Andromeda and other galaxies as independent systems, astronomers laid the foundation for modern cosmology and the study of the universe on large scales. Looking forward, the impending collision between the Milky Way and Andromeda presents a unique opportunity to study galaxy mergers and their impact on cosmic evolution. Although the collision won't occur for another few billion years, simulations and theoretical models predict a dramatic interaction between the two galaxies. When the Milky Way and Andromeda eventually collide, their gravitational forces will distort each other's shapes and structures. Stars and gas clouds will be thrown into new orbits, triggering waves of star formation and potentially disrupting existing planetary systems. Despite the vast distances between stars, some may be ejected from their galaxies altogether, while others could be captured in new orbits around the merged galaxy's center. The collision will also affect the supermassive black holes at the cores of both galaxies. These behemoths, each millions to billions of times more massive than the Sun, will eventually spiral towards each other due to gravitational interactions. Their final merger will produce powerful gravitational waves, which could be detected by future observatories on Earth. The merger of supermassive black holes is not only a cosmic spectacle but also a crucial event for understanding the nature of black holes and their role in galaxy evolution. The energy released during the merger will be immense, potentially influencing the surrounding gas and stars and shaping the future evolution of the newly formed galaxy. Furthermore, the merger's aftermath will transform the Milky Way Andromeda system into a single, larger galaxy known informally as Milkomeda or Milkdromeda. The new galaxy will likely exhibit characteristics of both progenitors, blending their stellar populations, dark matter halos, and structural features into a unique cosmic entity. Studying the Milkomeda merger will provide insights into the processes of galaxy formation, evolution, and diversity observed across the universe. It will also offer clues about the fate of our own solar system and the potential for life in merged galaxies. The collision between the Milky Way and Andromeda underscores the dynamic and evolving nature of the universe on cosmic timescales. It serves as a reminder of the intricate interplay between galaxies, dark matter, and black holes in shaping the cosmos we observe today. As we continue to explore and study Andromeda and other galaxies, we deepen our understanding of the universe's origins, evolution, and future. Each new discovery brings us closer to unraveling the mysteries of the cosmos and our place within it, from the smallest stars to the largest galactic structures. In conclusion, the study of Andromeda Galaxy remains a cornerstone of modern astronomy, offering profound insights into galaxy formation, evolution, and cosmic interactions. From its stellar populations to its dark matter content and impending collision with the Milky Way, Andromeda continues to captivate scientists and skywatchers alike, inspiring exploration and discovery in the quest to understand the universe.